Okay, in this video, I will use another numerical example, the same context but different numbers. So now let's think about a aspirin with 325 milligrams, a larger dosage aspirin. So we are going to test if the true mean equals 325 or not. Okay, so and other numbers do not change. We will assume that our scale is still standard deviation of 5, like a measurement error is 5, and the sample size is 100, and the significance level is 5%. So those numbers do not change, but I change it to null hypothesis only. And we are going to do these 4 steps. This is what we are going to do in this example. First, we will calculate the critical values, which is pretty simple, and then type 1 error, type 2 error probabilities. And then finally, we will do numerical experiment. What happens if alpha changes? We will calculate those error probabilities for different alphas. Okay. First, it's simple. Like, what is the critical values? So it's your exercise. So pause the video if you need more time. It follows the same formula we used before, and we use 5%. So z alpha over 2 is again 1.96. Standard error is the same as before, 5 over square root of 100. So actually the margin is the same as our first example, because alpha and standard deviation and sample size are the same. The only difference is the center. It's only like the interval, the critical values shift parallel. Okay. So you get critical values in this form, like this. So we are going to use these critical values as long as alpha, mu, like the hypothesis, null hypothesis, alpha, standard deviation, and sample size do not change, right? So the critical values will be maintained throughout the example. Given the critical values, it is your exercise again. What is the type 1 error probability? Calculate the probability by yourself. Okay, so if you need more time, again, pause the video now. The answer is 5%. You don't need any algebra because, as I said, type 1 error probability is defined. It's just another definition of the significance level, right? So they are the same thing, 5%. If they are different, then there is some error, like the statistical errors, or like hypothesis testing has some error, right? They must be the same. So the answer is B. Always equals the significance level. Okay. This is the simple solution. So up to here, nothing special. You are going to make 5% type 1 error. And then now we are going to calculate the type 2 error probability, which is more involved and like it requires algebra. You have to do the algebra. So let me start from the very beginning. So the definition of the type 2 error is when you do not reject wrong null hypothesis. That is the definition. And we are going to calculate the probability of type 2 error. So what probability do you need to calculate? Okay. When you do not reject the null hypothesis, when you do not for to not reject the null hypothesis, your sample average, observed sample average, must be between the lower critical value and the upper critical value, right? So the answer is A. Okay. So actually, to calculate this, you have to calculate E. So E is also a correct answer, right? They are the same probability, but just our intuition is that when the sample average is in between two critical values, that is when you do not reject the null hypothesis, and that's when you make type 2 errors. Okay, so that's that is type 2 error probability. But here, another thing you need to think about is, okay, so type 2 error probability happens when you don't reject and at the same time the null hypothesis is wrong. Then you have to set up how wrong your null hypothesis is. So our null hypothesis is 325. Then we have to choose one number that is different from 325. So now we are going to choose 324, just as an example, right? So this means the null hypothesis is wrong. And in this case, it's really an algebra question, algebra practice. You have to find the type 2 error probability. Do it by yourself. And basically, you are going to calculate this probability. You will need to standardize the numbers and then use a standard normal calculator. Okay? Okay, so let me show you the answer. So you are going to standardize, but you are going to use 324 for the mean, actual mean, so true mean for standardization, right? So, and the denominator, standard error, is standard deviation divided by the sample size. There is no difference here. So you just calculate these two numbers, which is 0.04 up to 3.96. And you find these numbers from this probability from Excel, right? That is 48.4%, right? In case you, we learned how to calculate this probability from chapter 6, okay? So this means you are going to make, there is 1 milligram difference, and you will fail to detect the difference with this much probability, 48%, okay? So it depends on your significance level and your standard error and sample size, and also your alpha, right? And also how different the truth is. Okay. Now I will try another number. Like previously, there was only 1 milligram difference, so it was hard to detect. Now think about a bigger difference. Now the true mean was actually 320 milligram, 5 milligrams smaller than it's supposed to be, right? Then in this case, what is the type 2 error probability? Follow the same algebra and try it by yourself. Okay, so let me turn the page. It is just another different standardization. Standardize with 320, because now center is 320, not 324 or 5. So you use this number here. And then after standardization, probability, it is probability between 8 something and 11 something, nearly 8 to 12. So you this in the scale of standard normal distribution, 8 and 12 are extremely large number. Outside 4 or 5 is nearly impossible to happen, right? So on Excel, if you use a normal distribution calculator, you will find it's 0.00000%. So it shows that you are not going to make any error, nearly no possibility of type 2 error in this case, because 5 milligrams is too obvious. It is so obvious that you cannot fail to detect that. If you see a smaller tablet, you can tell this from the scale, right? So you cannot miss it, you cannot make a mistake in this case. So it illustrates that type 2 error probability depends on how difficult to detect the difference. That's the main idea. Okay, so and we just need to calculate the probability accordingly based on different standardization. So the difference comes in to the step of standardization. So that's the only difference. Okay, so I just explained the idea. When the difference is small, your type 2 error probability could be 48, but when the difference becomes larger, your type 2 error probability goes away. It's easy to detect. Okay, smaller difference is harder to detect, which is pretty obvious. So then we call this the power of a test. Like, so the power is the flip side of type 2 error. So the power is defined as the probability of rejecting a wrong hypothesis. Like, if you can detect a wrong null hypothesis, that is the power. We call that power. So uh, when the null hypothesis is wrong, if you correctly reject it, that is power. If you fail to reject it, that is type 2 error, right? So power is just 100% minus type 2 error probability. That is the definition, right? How well you detect a wrong null hypothesis, right? That's a simple, straightforward definition. And of course, the power depends on how different the truth is from the null hypothesis. Okay? So in this case, when the difference is 1 milligram, the power is about 52%. But when the difference is 5 milligram, the power is 99.999%. Okay? So that's how we define the power. Okay, this is the end of this numerical example. In the following video, I have another numerical example with binary distribution. So we will see you there, and bye.